This is going to be a short video where I compare the disk method with cylindrical shells. So let's take an example of a function. F of x is equal to 4 minus x squared. And first, let's set it up using the disk method. So what we want to do is we want to find the volume of revolution by taking 4 minus x squared, which is this curve right here, and rotating it around the x-axis. All right, so we're going to rotate that around the x-axis. So we need to know where it's going to intercept the x-axis, and so that's easy to find, and that would be at 2. So our bounds of integration along the x-axis are 0 and 2. Now what I like to do, and I explain this in my notes, is I like to draw a little rectangle that would be representative of what I'm doing, okay? So when I'm integrating here, I'm creating a little rectangle, right? And we're rotating that rectangle around the x-axis, creating a disk. So I have my bounds of integration. I have my radius, because remember with the disk method, the radius is the function value. Unless we're rotating it around some other axis other than the x-axis or the y-axis. So in this case, we are rotating it around the x-axis, so the radius is just the function value. So putting this together, I have my basic integral. Now I could have stopped here because this is really all I was interested in doing. This is how I would be setting up my integral, right? Because volume is equal to the integral from a to b of pi r squared dx, where r is f of x, so it's the volume is equal to pi times the integral from a to b of f of x squared dx. And so that's what we have right here. And so I just went through and I expanded the binomial 4 minus x squared to get this. I then found the antiderivatives, and then I evaluated the antiderivatives, but I did not simplify it further by getting common fractions. But the reason I say that we could have stopped right here is because I entered this into Desmos. So what I would like you guys to do is enter that integral into Desmos and see what you get. You're going to get a decimal number. All right, so now let's do the same problem by using cylindrical shells. To set this up using cylindrical shells, we're going to make our rectangles going the opposite way, right? Because the reason is we're rotating it around the x-axis. Still rotating it around the x-axis. We're rotating this area around the x-axis, but we're creating shells, not disks. So when you're using the cylindrical shells method, the length of your rectangles will always be parallel to your axis of rotation, right? The length of the rectangles will always be parallel to the axis of rotation. And so that's why I make these little rectangles. I don't really need the rectangle for anything except just to kind of orient myself. And so my bounds of integration now are going to be along the y-axis. The bounds of integration are always perpendicular to your length of your rectangle. So my bounds of integration are from y is less than or equal to 0, and y is less than or equal to 4, greater than or equal to 0. I then also, because the bounds of integration we're integrating with respect to the y-axis, I have to go through and rewrite this from y as a function of x to x is a function of y. So x is equal to the square root of 4 minus y. So I have everything that I need. And so now remember that volume is equal to the integral of ab times 2 pi x f of x, or 2 pi y f of y dy. And so here is my basic formula. My integral. Set up the integral. My 2 pi comes out because it's a constant. On the y-axis, I'm integrating from 0 to 4. And then I have my y. And so remember what y represents. Y, this right here, represents the radius. Okay, the radius of your cylindrical shell. The radius of the cylindrical shell is from the x-axis to your rectangle. And so that is a distance of y. And then remember what the function is. Okay, the function is the height of the rectangle. Okay, the height of the rectangle is your function value, f of y. All right, so you can go through, you're going to have to actually do use substitution to evaluate this, and I didn't go all the way with it again. I just started it so you could see how we would start it. And I got it in terms of my use, but I stopped. But what I'm really interested for you guys to be doing is to put this in Desmos. Put this in Desmos. And then you're going to compare it to what you got when you put this, the first one, in Desmos. You should get the exact same thing. Desmos will give you the same exact decimal answer for both of these integral problems, for this one and for this one down here. Okay, so whether you should be able to do all the integration, but the important idea that I want you to see is even though you use 2 completely different methods, and even though you set it up completely different, one was with respect to y and integrating with respect to y using cylindrical shells, the other one was with respect to x using the disk method, you still end up with the same volume. 2 different methods, 2 different orientations for your integration, but you get the same result. All right, that's what I want you to get out of this. Enjoy.